Excellent. All right, so let's get started. Welcome back, everyone, to what's become now the security track, which is great. Always good fun. Yeah, thanks for being here with us in this after lunch slot. I know everyone's always really awake during this slot, so we'll try and keep it light, we'll try and keep it interesting, and we're going to talk about how we can build security continuously into our development processes. So yeah, let's get started.
Okay, so Josh and I are security people, so we're probably biased when we say that, but it feels like we hear about security all the time. We have a security team in our companies that's dedicated just to security. We have automatic scanning tools that scan our code to find security problems. And we have all those guidelines and everything, and we just keep hearing about it. But on the other hand, we keep hearing about security breaches, embarrassing security breaches. Why is that? What's the problem here? So we have all those guidelines and best practices and scanning tools, but they all work under this one assumption, that we're all pretty much the same. We all write code that's pretty much the same. We all use the same popular frameworks. We all copy the same code snippets from Stack Overflow, and it's just the same. So if we follow those best practices and use those scanning tools, then we should be just fine, right? Well, we're not. So until AI writes all our code for us, we're still unique snowflakes with our own unique legacy code that everybody's scared to go near, and with our own corporate bureaucracy that prevents us from touching any APIs, and with our own unique business logic. That's why we have our own unique company, after all. So with time, each company comes up with its own custom rules, its own custom guidelines. For example, don't use this function. We can't delete it from our code base because some legacy code still depends on it, but you shouldn't use it anymore because it's not secure. We have a more secure version. Use only that. And remember, don't use this old function. Or we have this popular framework that we use, open source. We should use it only with our own wrapper. We can't use it without the wrapper. Remember, don't use it without it. And it solves the first problem, that generic tools, generic guidelines miss out on our own unique problems, but it creates a new problem. Who enforces all those rules? Who remembers all those rules? Is it the developers when they do code reviews? They need to check all those problems, or is it the security team that needs to go over our code and check it? It just all creates one big headache. And today, Josh and I are here to offer you a relief. So who are we and what's our motivation? My name is Michal Kamensky. I work at Bound Security with Josh, and I'm a security researcher. I also believe that security should be part of the community. It should work side by side with developers. And because of that, I also volunteer at a Hackerot initiative that helps women to get into cybersecurity. If any of you wants to hear any details, come talk to me afterwards. And I also helped organize this year's BSIDS TLV, which is a security conference. And that's it. Josh?
Yeah, so my name is Josh Grossman. I also work at Bound Security with Michal. I've worked in different areas of security, sort of finally specializing in software security for several years now. And again, my passion, what's important to me is, again, how we can make it easier for developers, how we can make it more seamless for developers. I'm also involved in the community. I'm involved in the OWASP community, the Open Worldwide Application Security Project. So if anyone has questions about OWASP or OWASP projects, then please see me afterwards. We also run the second largest security conference in Israel, the OWASP Israel conference. But yeah, so we both work for Bounce, and we were told to be very clear, we're not trying to sell something here, we're not trying to sell a product. What we're trying to sell is ideas and hopefully thoughts that can give you things that you can use in your day jobs when you get back. So that's who we are. So what's our motivation? So we called the talk Omniscient AppSec. So if we look at the dictionary definition of omniscient, in case anyone's not familiar with it, having infinite awareness, understanding, and insight, or possessed of universal or complete knowledge. Okay, so the idea is we can see everything. So what does that mean in our case? So the way we want to structure this talk is in 3 key sections. We want to enforce, from a security perspective, everything, everywhere, all of the time. So what do I mean by that? So we can do everything. We want to enforce custom security solutions that match our unique Snowflake code. We want to be doing it everywhere. We want to be doing it across our code base or multiple code bases. We can't just be looking one by one, line by line. We need to be able to cover our entire code base. And we want to do it all the time. We want to be able to do it every time we process our code, every time we have a CI run. So in this talk, we're going to go through those 3 sections and sort of illustrate how we can do that. What do I mean by a custom solution? So if we think about security vulnerabilities, we can think about 2 different types of security vulnerabilities, roughly speaking. We've got generic security vulnerabilities, ones that are very well known, things like cross-site scripting, SQL injection, things you'd find in the OWASP top 10 that are quite well known, sort of off-the-shelf vulnerabilities. And there are also application-specific vulnerabilities. These are vulnerabilities that are specific to the way that our application works. Now, this could be a question around how our application enforces our application's business logic. This could be how we enforce permissions within our application, like we saw with Gabriel this morning. These can be vulnerabilities that are very specific to exactly the way our code works and to the flow of our code. Now, for each of these vulnerabilities, types of vulnerabilities, we can either have a very sort of generic, off-the-shelf solution, something that's like a one-liner, very well-known, here's how you fix SQL injection in Python. Or we might have to come up with some sort of bespoke solution, some sort of way of doing it that's specific to the way our code works, specific to the way our application works. So if we look at this example, who here knows what, if you can see the code, it's a little bit small, what vulnerability is in this first line of code here? You can stick up your hand if you've got any ideas, or you can just shout it out. SQL injection, nice, okay. So this first line has an SQL injection vulnerability. If someone can put some dangerous content into that username field, like with including a single quote that's going to finish off that query, start off another query, it might end up doing something we didn't expect. Now on the second line here, the second version of cursor.execute, we've got the fix. The query has been parameterized, so that username is going to be treated like data, regardless of what happens. We're not going to be able to break out of that username field and start making changes to the query itself. So that's a very simple generic vulnerability with a very simple generic solution. So this sort of fits into this top left box here for a generic solution. Unfortunately, a lot of places aren't like that. If we have got vulnerabilities like that, we've got tools like SAST, Static Application Security Testing, which will look through our code and find vulnerabilities in the code and say, okay, this is a problem. So in Python, we've got pylint and bandit. There are various other commercial tools as well that you may recognize or have nightmares about, depending on how involved in security you've been. Apologize if anyone's traumatized. And these tools are going to be quite good at finding these sort of generic vulnerabilities and seeing whether we fix them with the right generic solution or not. And we'd hope that would fix us. This is what the SAST vendor told us. It'll solve all your security problems, right? But no, because we have these other 2 areas as well. SAST tools assume that everything is a generic vulnerability and a generic fix, and it can detect that regardless of what code base it is and what application it is. But as we've seen, we have situations where we have to have a specific fix. So maybe the SAST tool will recognize the vulnerability but won't know whether we fixed it or not. And we also have our application-specific vulnerabilities where we're almost certainly going to have a specific bespoke mitigation that the SAST tool probably won't recognize the vulnerability or the mitigation. So let's look at another example here. Anyone want to give a guess as to what sort of vulnerability is being hinted at here? You can shout it out again if you want. Path traversal, yeah. So here we can see we've got a path traversal issue. If someone puts in some sort of dangerous input, like we can see down here, into that input field, then instead of reading a file from within our safe folder, it's going to break out of that folder and it's going to read a file from a different folder. Now this is a pretty well-known vulnerability. I'd call it a generic vulnerability. Yeah, it's well-known, it's very common, but the fix is going to depend on how we're using files, how we're storing files. So for example, I can create a basic sanitization function here, which I've called sanitize input. And that's going to strip out those past reversal characters, those dots and slashes. And I can't guarantee it's going to work in every single case in this case. It's not going to work in every single case. But the idea is just to illustrate it. The idea is we've now got something that will work in our case, but we've had to write this sanitization ourselves. There's no off-the-shelf, one-liner, here's how you fix this. So it ends up with a generic vulnerability, but with a specific fix. And that means we've got a custom solution. So even if a SaaS tool understands that we've got a vulnerability here, it's not going to know whether we're actually mitigating that vulnerability or not. So we might end up with a whole load of false positives because it says, oh, you've got this past reversal vulnerability. I'm like, no, I sanitized it. I created a sanitization function. I put it in my code. Well, why are you still shouting at me? So this is the idea when we talk about a custom solution. We have problems in our code that aren't common to everyone, solutions that aren't common to everyone. We need to have a way of addressing those solutions. And once we've got a way of addressing those solutions and addressing that problem with a solution, we need to figure out how are we going to find when this is happening in our code and how we're going to make sure it doesn't happen again. So that brings us to the next stage of everywhere, looking across our entire code base.
So how are we going to do that everywhere part? How are we going to scan all of our code base? For this talk, we've used a tool called Semgrep. It's a free open source tool that all of you can use. And what it basically does is it finds patterns in your code. But it's not just a simple control F search. If it was, you could just use grep, but it's Semgrep because it also understands the semantics of your code. It understands what classes are, what functions are, the flow of variables between functions, and all that. So again, we used it because it's free. It's simple to learn, simple to use, but there are also alternatives you could use. If you have proprietary SaaS tools in your companies that you can customize the rule set, you can use that as well. Also, there is GitHub's CodeQL. It's free if your code is open source on GitHub. Otherwise, it costs money, so that's why we didn't use it for our demonstration today. And if you hate your life or something, you can use grep, or if you have a very talented cat. That's another option. So that's the everywhere. How are we going to scan everywhere? But what's our everywhere in this talk? What code base are we scanning? So it all starts with a few tech bros who were sitting in their apartment during 2021 COVID quarantine, and they were really, really bored. They noticed their cat has an interest in their chess, in the chess pieces, in knocking them off the chessboard, and they decided, why not develop an app that will teach cats how to play chess? So it might sound weird to you, who would invest in an app that teaches cats how to play chess? But remember, it's 2021. People invested in things a lot weirder, like NFTs or whatever. Also, they decided to call their app Cyber AI Transponster Chess. Who wouldn't invest in that? All they're missing is blockchain. That's perfect. And that's our cat chess app. That's an imaginary app, yeah, just making sure. And our examples are going to be based on this app.
So we've got 4 examples. We've given them each of them a name that's kind of connected to what they are. So the first one will look at creating a new overload to create a new secure version of a function. The second one will look at using decorators for security, for authorization. The third one will look at sanitizing input and how we detect unsanitized input. And the fourth one will look at libraries and what we can do when we've got a vulnerability in a library. So what each of these examples has in common is that each example is going to show some sort of vulnerability, something that's going to have a security impact in our application. One of the key parts here is that we could fix the vulnerability, but there's a very high risk that we might forget later on. We might add new code and forget to address this vulnerability there. We might end up making the same mistake again. So it's not enough just to make sure, okay, today we fixed this. We need to make sure that we're doing this all the way through. We've come up with a guideline. Here is how you do this securely. And now we're going to verify that we're doing this every time we're going to use the code in the future. Each example is kind of specific to our organization. It's not about specific vulnerabilities, generic vulnerabilities and generic fixes. Each example is going to have some sort of level of specificity to our application, which means we can't just use an off-the-shelf scanner to find the issue. And in each case, in order to make sure that we're doing it right, we can't just do this control F. We can't just do a search and look in our code. We need to have some sort of semantic aware search of our code base to make sure that we're doing it correctly. A few disclaimers. The code is a little contrived. We've obviously tried to focus on demonstrating examples. It's not perfect production level code. The idea is to make it clear, make it easy to understand the different points that we're trying to get across. So also apologies if we violated any style guides. The idea overall is to focus on these two key points. Number one, how we can come up with custom solutions to the problems that we see in our code bases. Number two, how we can check for that and how we can verify for that on an ongoing basis. So let's look at example number one, the wrong overload. So the year is 2023. Time has passed since 2021. Finances are a lot more difficult, and our cat chess app needs to be making money. So we've built functionality into our application to allow people to send money to the application. They can add new functionality or add new skins. And we've added this send transaction function to do that. But then we've looked at that and we thought, well, from a security perspective, we're sending money, it's a little bit dodgy. Maybe we want to make sure that that was definitely a valid transaction. Maybe we want to have some sort of signature to make sure that it's actually a real transaction. So someone's not going to replay the same thing over and over again, either by accident or on purpose, and not going to end up double spending, triple spending, or having some sort of financial fraud. We want to make sure we sign each transaction. The problem is we can't eliminate its functionality because we've already got clients using it. We don't want to break everyone's old versions of the application. We can't change the functionality name either, so we're a bit restricted in how we can fix this. So our proposed solution to try and make life easier is to create a new version of this function. It's not going to be strictly speaking overloaded, but something like overloading for the function. And we're going to add this signature that verifies did this transaction happen or not. So our new code looks like this. So we've now got a updated version of send transaction that has an optional checksum. So if they send if they don't send the checksum because it's the old version of the code, then it will go through to the old version of the code, and it will carry on as it did before. But if they do send the checksum, then it will go through and it will validate the checksum, and we can be sure that we've definitely done the right transaction. The transaction was valid. Now we can argue back and forth about the security merits of having this sort of in-between state whereby we allow both the old and the new, but at the moment it gives us a way of working towards a secure solution. But the problem is, now that we've got this, we want to make sure we're not writing new code using the old version of the function. How can we find examples where we're accidentally using the old version instead of the new version?
So this is our sample code. We have two cases here, one that we want to find and one that if we find it will be a false positive, so we don't want to find it. The first case is what we want to find. The send transaction that has only 3 parameters, no checksum. The comment above is a Semgrep thing that does unit testing for a rule. If the rule ID means we want to find it, the OK means we don't want to find it. So if any of this unit test fails, Semgrep will notify us, so we will be able to check a rule and modify it. So we want to find the first case, the send transaction function with 3 variables without a checksum, and we don't want to find the second case where we have a checksum. Why do we need a custom verification here? Because that's a specific solution to our company. A generic SaaS tool won't know there is a problem here and what we want to find. And we need an understanding of the semantics of the code. We need to understand what parameters are, what functions are. If we just look for send transaction on our code, we will have to go over all the cases where we use this function and check ourselves if we use the checksum or not. So here is our simple rule in Semgrep. Let's quickly go over the structure. We have the ID, which is just the name of the rule. We have the pattern, which is actually what we're looking for. We want to find some class that calls send transaction with 3 parameters. Everything that has $sign and uppercase letters, that's that's just, it could have said XYZ. It doesn't matter. It doesn't tell Semgrep that's a class. It just understands it because of the semantics of the code. Then we have the message, which Semgrep outputs every time it has a finding. And finally, the language we want to run this rule on. We want to run it on Python code. So we're looking for the send transaction function with just 3 parameters. And when we run it on our code, here we have only the yellow line. That's what Semgrep found. And both the rule ID and OK, the unit tests are in green. They passed.
OK. So let's look at another example. So we've got functionality in our application. We're letting our cats play chess against different opponents. And we've got various functionality we want to protect against misuse. We only want cats or end users that are allowed to use that functionality to actually do that. We need to add authorization to our application. Now, we don't want to do this in every single place separately. We saw lots of bad examples of this in this morning's talk, but we're going to use a slightly bad example, but at least we're going to have the implementation in one place. You don't want in every single function a load of if statements governing our permissions. But we do want to apply it to every single one of these functions that we're worried about, every one that we've got sensitive operations that we want to protect. So we're going to use decorators. We're going to use security decorators to define, OK, these are the functions that need to have authorization applied, and then we're going to implement the authorization logic in one place and then just apply it to all our other functions. So here's a very rough example. We have a permissions mechanism called require update per remission, which makes sure that the user who called that function is going to actually has that permission to do that update operation, do that sensitive operation. Then we can see we've applied that to our sample function down here, lower down. So we've got our permissions logic in one place. We've got a decorator we can then use to apply that to different functions over the application. So we've solved our permissions problem, but if our application is small, then we're fine. OK, that's OK. We've got a small application. We've got it in a few places. We've applied it, and that's fine. But what happens when our application grows? What happens if we start adding extra functionality, extra games? Suddenly we've got 5, 10, 20, 30, 50, 100 different functions. How do we make sure we've not forgotten to apply this decorator somewhere? How do we make sure we've definitely covered all the different examples, all the different places where we have sensitive functionality? We've definitely covered them with the decorator to enforce permissions.
So that's our sample code. First of all of our sensitive functions are in one class, the sensitive functions class. We have the first function that has the security decorator. This function updates the scoreboard after a game is finished. We want only authorized people to be able to update it, or our opponent will be able to say that he won even though he lost. And the other case, where we don't have a security decorator, that's what we want our rule to find. It's the next move. Again, we don't want our opponent to be able to make the next move for our cat and say, for example, that he sacrificed his queen. So why do we need a custom solution here? Because there needs to be an understanding of the solution that we decided to apply. We don't want to have a bunch of false positives from a generic scanning tool if it even understands that those functions need a check for permissions. And we can just scan our code with our eyes and look if we forgot a decorator, but that's not a really good solution. So that's the rule that we have here. What are we looking for? We're looking, first of all, for a pattern of a function definition. But function definitions can be really long. We don't want Semgrep to return to us all of those lines of code, so we tell it to focus on the meta variable function. So it will just highlight the first line of the function definition. Then we tell it that this pattern is not inside a decorator and then a function definition. This means it won't return to us only cases where we remembered to use the decorator. And finally, we tell it to look only in this class of sensitive functions, because if it will look across all of our code base, there are a bunch of function definitions. We don't want to find all of them. And when we run this rule, we find only the next move cat. So no one is able to say that our tabby took with its queen on h6, because our tabby is smarter than that.
OK, so let's look at example number 3 now. So we now need to put some sort of dangerous functionality into our application. We want to be able to send messages to, or to check that other opponents or the other users of the application are still alive. We're going to send them a ping message via the operating system. That means we need to execute an operating system command. And we're going to have to pass that command the address of the other side that we want to test. That is address the other side that we want to check. Also, we need to make sure we're doing this carefully, because if we allow someone to provide uncontrolled input to an operating system level command, then they can end up executing other commands, not just a command that we wanted, and doing all sorts of nasty things on our web application server or the wider network. So we need to sanitize it, we need to protect it. But the problem is that we've got this implementation of the function we want to use, it's called run ping, and we can't change that. We can't mess around with the functionality of that function, we can't add sanitization within it, we can't change the signature, we can't add typing. We're stuck with this particular implementation, we have to make sure we're sanitizing it before we use it. So here's our run ping function that we can't touch. It's quite straightforward, it takes input and runs it on the command line in the ping command. If we just allow anything to go to this function, it's going to go very badly for us. Someone's going to end up running dangerous code on the OS. So in our basic example here, we're getting input from somewhere. It's a simplified example, but we're getting input from somewhere and we're sending it to that run ping function. This obviously isn't safe, so we want to create a sanitization function. We're going to create something that's going to make that content safe, and then we have to make sure we use that function before we use run ping. So here's our updated code. We've now added the sanitize it. I've deliberately not implemented this because, again, trying to fix this sort of issue, trying to apply this particular mitigation is very dependent on the OS and other factors about what you actually want to pass to the function. But we've got a sanitization function. We've got something that's going to make that input safe. So now, the first time round, we can see it's the same as before. It's just getting the input and it's running it through run ping, and that's dangerous and that's bad. And in the second example, we're now running it through a sanitizer first. We've run it through that sanitization function, and only then are we passing it to run ping. So now we know we're protected against dangerous input. Now we know that input isn't going to ruin our day. So we've got the solution. We've got a sanitization function. We need to run this every time we run ping. But again, what happens if someone else uses run ping somewhere else? What happens if they forget that guideline they have to apply that sanitization? We know that now today, but how are we going to make sure that we don't forget to do this in the future when we use run ping somewhere else?
So let's take a look at our sample code. We have the first case where we start in get input and end up in run ping. That's something that we want to find because we forgot to sanitize it. And the other case, we started at the same get input and end up in run ping, but we first go through sanitize it. So this case is okay, we don't want to find it. Why do we need a custom solution here? Because generally, SaaS tools are not aware of our personal sanitization functions. Unless we use sanitization that is generic, they will miss on it and give us a lot of false positives. So that's why we need a custom solution here. We need a rule to be able to follow a flow, to be aware of something starting in a source. In our case, that's the input. That's our source where dangerous input is coming from, and ends up in a sink. A sink is something that the source ends up in, that's something that came from the source ends up in, and can perform dangerous activities. And we needed to be aware of our sanitizers, which, in case we went through them, they won't give us back the results. So we're going to use something in Semgrep that's called taint mode. It follows sources, sinks, and sanitizers. So our sources is the Python input function, our sink is the run ping function, and our sanitizers are the sanitize it. So it will find everything that starts in the input, ends up in run ping, and it will omit from the results the cases where we went first through sanitize it. When we run this tool on our code, we find only the run ping case. That's what we want to find. And to our last example.
Okay. So example number 4 is about a vulnerable library. This one's a little bit different now. In this situation, we want to be able to store save game files from our cat chess game, store them in a compressed file, and then decompress them afterwards. So in order to support file compression and decompression, we're using a wrapper around the 7-zip application called Py7ZR. Unfortunately, we've got a vulnerable version of that library. Now, ideally, when we've got a vulnerable library, we want to upgrade the library. But let's say we're in some sort of intermediate stage, we can't do that for some reason, we can't upgrade yet. But what we think is that we're not using the vulnerable part of the library. We think we're using part of the library, but not the bit that's actually vulnerable to this particular vulnerability. So if we look at the explanation for the National Vulnerability Database, we can see that there's a vulnerability in the extract all function. So working for idea is that if we're using the extract all function, then we've got a problem, we're vulnerable, we need to either not do that or upgrade the library. But if we're not using extract all, then maybe we're okay, maybe we're safe. So what we want to try and do here is we want to try and delay the upgrade, which, again, I'm not sure I'd recommend, but let's say that's the cards that we've been dealt for now. We want to delay the upgrade, and we want to search across the code base to make sure we're not using this extract all function somewhere in our code base. Again, the question is, okay, we can verify that today, we can verify that now, we know that we're not doing it now, but how are we going to make sure we don't, in the future, start using this dangerous extract all function?
So here is our sample code. We have two cases where we're using some that function from the 7zip library that ends up in the extract all, those cases that we want to find. We also have a compress game function where we use the same library, but we use a different function that is not vulnerable. And the last case we have is we're not using the vulnerable library, but we use extract all function. That's a different function that we just named the same way. We don't want to find that. Why do we even need a custom solution here? That's what scanning tools are for finding vulnerable libraries. So SAS tools usually don't look for vulnerable libraries. They just look for patterns in our code that are vulnerable. And ACA tools that are looking for vulnerable libraries and tell us about them, they don't look for vulnerable functions usually. So what are we going to do here is use, again, taint mode. And our source is going to be something that comes from the 7zip library and ends up in the extract all function. So we won't find any cases where we used extract all that's not from the library, and we won't find anything that is from the library but is not a vulnerable function. And when we run this tool, we find only the first two cases that are vulnerable. So all of our examples use Semgrep. So just a few limitations of Semgrep to be perfectly candid about this tool. So it has no cross-file scanning in Python. They do implement it in other languages, but they don't have it for Python yet. Also, they don't support types in Python for now.
Okay. So we've talked about everything. We've talked about various different custom solutions. We've seen examples of, okay, here's a problem. How do we fix this with a custom solution? How are we going to think, okay, we can't just find something off the internet. We need to implement this in a way that works for our organization. We looked at everywhere. We looked at how can we scan this across an entire code base? How can we scan this across multiple code bases? So that brings us to the final question of, okay, well, how can we do this all the time? How can we do this on an ongoing basis? So I didn't want to show a live demo because we're using the conference venue's PC, but I've pulled out a walkthrough of how to actually use this in a CI process. I've chosen GitHub Actions because it's nicely straightforward. I think a fair number of people use this. And we can see how we can actually apply it. So we can see here a GitHub action file here. This is the file that defines what the GitHub action should do, what it should do when we actually run this action on our code. This one's called Semgrep plain. It's defined, in this example, just to run either manually or to run every time someone pushes to one of the main branches. And then what's it going to do? It's going to use the Semgrep basic image, and it's going to run a couple of simple commands to scan our code base using the rules we've defined. You'll recognize the names of the rules from the examples, 1, 2, 3, 4 that we went through. As you might imagine, the Semgrep rules are in our repository. The code that we use as example code is in our repository. This is going to run those Semgrep rules on the code each time we do something in that repository. This repository, by the way, is on our public GitHub. We'll put up a link to it at the end so you can take a look and play around for yourselves afterwards. So if we look at the log from that GitHub action, we've now got a log showing, okay, we ran these rules, and here are the exceptions. We've got 3 places in the code where, as the example, one rule picked up issues. It picked up 3 places where send transactions being used with the wrong number of parameters. As we go further down the log, we see the different rules that it picked up on it. We've configured it so it comes back as a failed workflow, and we can handle that however we want to handle that. So that's one way of seeing it. Obviously, it's not super convenient because it's just in the log of a GitHub action. We've got to sort of dig around a little bit to find the results. This second log example is from a different action, which is similar, but this action will output the results from Semgrep to a particular format called sarif. Sarif is a sort of interchange format for code security scanning results. It's going to take that sarif file, it's going to upload it into GitHub Advanced Security. So now we don't see the results from doing that scanning in the GitHub Actions log, but we're going to see it somewhere else instead in GitHub Advanced Security Dashboard. So where's it actually gone? So if we go back to our GitHub repository, we can see we've got this tab along the top called Security. I don't know if you've noticed this on your own repositories. You may well be familiar with it already on your own repositories. There are various different various different settings in here related to the security as a code in your repository. Now, if we look down the side here, we've got code scanning. Code scanning is one of the options. Obviously, GitHub has their own code scanning, but we've just put our own code scanning results into here instead. So we can see now that we've got 7 results that have come up from that code scanning exercise. So if we dig into that code scanning tab, we can now see the results that have actually come up. We can see from the results from the rule checking for it, we created an exercise 1, the rule we created an exercise 4, exercise 3, etc. If we dig into one of those rules, we can then see it's picked up the same information. It's given us the same thing we needed to know. It's shown us what the line of code is, where it found that issue, what the actual issue is based on the description that we wrote into our rule, and it's fully integrated into our code repository. So if we now click into that particular link there, we can go to that code file and figure out, okay, well, why have we violated this rule? Why have we violated this alert? So we've now got a situation where we're doing the scanning, we're checking for our custom rules, we're checking for our custom guidelines, and we've got alerts coming up inside our existing workflow to tell us, okay, you've got a problem, one of the guidelines that you've defined has been violated, you need to decide what to do about it. So the example we showed was in GitHub Actions, just because it's the easiest to demonstrate and easiest to give you to look at separately as well. But again, it can fit into any CI process, any workflow process. To run Semgrep, you're just running pretty much one command, maybe 2 commands if you want to use the pro version that has slightly more sophisticated scanning. There's no special processing you need to do to the code. A lot of the time when you want to do code scanning or use code scanning tools, you have to compile the code, or you have to process it or transform it or package it up in some special way. This is just happening as a one-liner on our raw code as it is in our repository. We then get an alert when our rules are violated, when someone breaks one of the rules we've defined, and we can decide we're going to break that CI process, or we're just going to set up some sort of out-of-band process to alert on that. And in this way, we can make sure we're enforcing these rules, not just now, but going forward as well. So the key takeaways in summary: not every vulnerability has a generic solution, and we need to remember that our code is special, and therefore we're going to have our own special magical vulnerabilities that we're going to need to figure out how to address. And even if those vulnerabilities are generic, we may have to fix them in a particular way that might not be standard. We might have to come up with it ourselves, and scanning tools might not recognize that. We need to be able to check for this sort of thing across our entire code base. We need a semantic-aware way of doing that. We need to be able to verify, are we enforcing this rule correctly or not? Again, the regular off-the-shelf tools won't help with that. And we need to be able to do this all the time on an ongoing basis. We want to build this into our CI, run it through on every code event, on every code build, on every code operation that happens, to make sure that we're checking today, tomorrow, the next day, next month. We're not forgetting these guidelines. We're not worrying about who's enforcing these guidelines. We're not worrying about whose responsibility it is to check for this sort of thing. It's being done automatically within our existing flow.
So we hope you learned today how to help your cats play chess securely. And we have here a QR code that goes to our repository where all the rules are, or the sample codes is, and our slides are there as well, so you'll be able to go through them. And that's it. If you have any questions, we are going to stick here during the break, and you're welcome to come ask us anything.